Okay, in this section we talk about the integration of a function. In the last section we talk about the analytical function, means that the function can be differentiated. Now we try to integrate the function in this section. Okay, for example, we have a curve in the xy plane. We call it C. Okay, and then we integrate a function along a curve C. See here, this function can be decomposed in the real and imaginary part, and dz can also be decomposed into the real and imaginary part. And then we multiply this by this to get the result here, and then we try to identify the real part and the imaginary part by this direct multiplication. And then we put this expression back to here. And then we will find that this integration along a curve C can be expressed as a real part and the imaginary part. Okay? We will talk about this expression later, but before this, let us look at a concrete example. In example 1, we have a function fz equal to z minus z0 n power. But here I emphasize that n not equal to minus 1. You will understand the reason later. Okay, and then we adopt the curve here which is a circle. Okay, the center of the circle is z0, c naught, and then the radius is r naught. We draw the picture here. We have the circle C here, and then this is the center, and then this is a typical point along the circle. We can draw a vector and vector here, and then we see that the vector connected z and z0 is z minus z0. Okay. Now we can apply a local coordinate to the center of the circle here. We draw a local coordinate here, and then this vector can have an angle theta, and in this way we can express our term z minus z0 in terms of theta and r naught. Okay, the radius of this circle is r naught, and of course this is the same circle, the radius is also r naught. So in this way, z minus z0 can be expressed in here in the right angle, right upper side, right upper side. Okay, z minus z0 equal to r naught exponential I theta. Why? Because in this local coordinate, we can draw a picture here. Z minus z0, the length is r naught, and then we can decompose it into the vertical component r naught sine theta and the horizontal component r naught cosine theta. Okay, and then we write the horizontal part here and the vertical part here, and then we grouping the term, but this is just the exponential function. Okay, so we have z minus z0 equal to r naught exponential I theta. This is a very important expression. We'll use it later. And then we try to calculate the detail of this integration. See here, z minus z0 is r naught exponential I theta, and dz is just I r naught exponential I theta d theta. Why? Because we take the differentiation at the right side. This becomes dz, but z0 will be deleted because it is a constant. Okay, and then we take the differentiation in the left side to get this dz. to the right side, we differentiate it, but R naught is a constant, so we just write here. And then we differentiate this function to get I exponential I theta d theta. Okay? And then we multiply this term with this term to get this one with a n power here. Okay? And finally, we can reorganize all these terms to get this final result. And then we have an n power here, so we have n plus 1 power because we have also R naught here. So R naught n plus 1 power. And this exponential I theta n power become exponential n theta, but when it is multiplied by exponential I theta, it becomes exponential I n plus 1 theta. Okay, we put all this expression into here to get this one. And then now we understand that our integration along C become the integration with respect to theta only. Why? Because we are integrating along a circle. So the only variable is theta. The radius won't be variated. Okay? So we get this simple expression, and then we take the constant out of the integration, and then integrate this function to get this term. After this, we just express this function in the real part and the imaginary part, and then put the lower limit and the upper limit here, or lower bound and the upper bound here. Okay, and then we put the upper bound into this function and write it here, and minus the lower bound here. And see, we have the psi something pi, so it is 0. Your psi function, when you have some pi inside psi function, you become 0. And psi 0 is 0. And cosine 0 is 1. And cosine 2 n plus 1 pi is 1 too. So we get the result 1 minus 1 here. So finally, we understand that the integration is equal to 0. So it is very important that n is not equal to minus 1, because see here, we have a n plus 1 in the lower part of the fraction. So n cannot be minus 1. No, it is not permitted. N cannot be minus 1. So for n not minus 1, we get this integration 0. So we want to see what will be the value if n equal to minus 1. We will do it again in the next example. Thank you. Yesterday, we talked about one example for the integration of this special function. When n not equals minus 1, this integration will be 0. Okay, here C means that a circle with the center located at Z0, and the radius is just R naught. Okay, we say that when n not equal to minus 1, then this integration will be 0. We had already proven this fact in the last example. Now I want to prove that when n equals minus 1, this integration will not be 0. Actually, later we will see here at the right hand side, this the integration of this function will be equal to 2 pi I. Okay, here minus 1 equal n minus 1. So we replace n by minus 1 here. Okay, let me explain the details step by step. Here again, we draw the circle like this, and this is the center, and this is the radius. And we try to define a local coordinate with the origin of the coordinate located at z0. And then we define the angle theta like this. And then we have the triangular relation. We draw the triangle out here to make it more clearly. And then this R lot is the length between the vector connecting z0 to z. Okay, this is a vector. It is just z minus z0. And then this is theta. The length of this vector is just r0. Okay, and the vertical component is just r0 sine theta. The horizontal component is r0 cosine theta. So in this way, this rectangular relation can be written in this way. Z minus z0 equal to the horizontal component plus I times the vertical component. And then we draw the R0 out from this bracket. And then apply the Euler formula to what? To regrouping these terms into here. We get the exponential expression. Okay, and then we try to differentiate this relation at the right hand side and the left hand side at the same time. See here, d here. We take the differentiation at the right hand side and the left hand side and the right hand side. We have the equality here. We take the differentiation at the left and also at the right. It is permitted. Okay, for this differentiation, z0 is just a constant. So the result of the differentiation is just equal 0. And then here, for the right hand side, R0 is a constant, so we just take it out of the differentiation. We only apply the differentiation to the exponential function. And then we use the chain rule here. The theta I, exponential I theta equal to the exponential I theta over the theta times the theta. This is called the chain rule. And then we multiply this term by I and divide it by I. So it is permitted because I and I will cancel out to each other. So we didn't change anything. Okay, we multiply I in the upper part and then multiply I in the lower part at the same time. So we will not change anything. Okay, and then for this this differentiation, you see that we are just performing the differentiation of exponential I theta with respect to exponential I theta, which is just a exponential I theta itself. In this way, we get the expression of dz as R0 times I times exponential I theta times d theta. And then we put this result into the integral. We look at the upper right side of the bracket. Okay, here dz is replaced by this term. We write dz as this term here, and then z minus 0 will be taken from here. Okay, we take z minus z0 to here. Okay, as a result, we see that this is a minus 1 power. So R0 and this 0 will be cancelled out to each other. So R0 is gone. Also, exponential I theta and exponential I theta will be cancelled out to each other. So exponential I theta will be gone too. Okay, will be deleted. So what remains is just the constant I, the imaginary number. Okay, the integration is easy now. It's just 2 pi. Okay. So in this way, we get the result. The integral of this term is equal to 2 pi I. The power of this term is -1. Okay, let us write down the summary of the previous two examples. Okay, we try to integrate this term z minus z0 of power n along a circle. Okay, this circle has the center z0 and the radius is r0. Okay, and then we integrate this function along this circle. Okay, and then if n not equal to -1, we have the result equals 0 in example 1. And if n equal to -1, we have the result equal to 2 pi I here. This formula, this result, and all this formula is very important. Very, very important. We try to expand this. See here, z0, the center of the circle, can be arbitrary. We can have any center, means that this result holds for any circle, okay, located at any center. And also the size, is not important too. You can have a very, very big circle or a very, very small circle. You still have this result. Okay, is it amazing? Okay, we look at here. We give you some easy example. For example, the center is located here. The circle is like that big. If you want to integrate this term of power 68, you don't have to do anything now. You know that it just equals 0 because we have already have the general formula. Okay, since 68 not equal to -1, so we have the result equals 0 directly. Now, if we integrate this term with the power equal to -1, then we know that the result will be equal to 2 pi I. Okay, we can apply this formula to another circle too. See, I just want to emphasize that this formula can apply to any circle with any center and any radius. Okay, for this little small, very cute, very lovely small circle, the center is z0 and the radius obviously is very small. And then if we integrate this term with power -1, we have 2 pi I result. Okay, is it amazing? We have arbitrary circle, and also the n power here can be any number. Okay, so it is a very useful result. I want to give you the important application of this formula right away. See here, we will come to this application later, but I just cannot wait to give you the application of this formula, because this formula is very, very beautiful. Let us look at here. What is the meaning of the result? The meaning of the result. We have the integration of this term equals 0 of 2 pi I when n have different number. Okay, what it mean? It means that if n equals 0, this is equal to 1. Okay, we are integrating 1. The result is 0. If n equals 1, we are integrating this linear term. The result is also 0, such and such. Now, what is this term? This term is just a typical term in a series, especially in a Taylor series. Okay, you learned Taylor series before. Let me do you learn that before? If you didn't learn this before, then please look at a standard book to pick up this knowledge, because Taylor series is a very famous knowledge for a undergraduate level student. Okay, let me show you one expression here. Any analytic function can be expressed in terms of a Taylor series in this way: fz equal to z0 plus z1 plus z2 times z minus 0 power 2 such and such. This is called the Taylor series. The point is, this function can be very arbitrary. We are saying any arbitrary function, so any function can be expressed in this way. Okay? Okay, any function. So we are not talking about a very special function. We are talking about infinitely many functions. Okay? Any function which is analytic can be expressed in this way. See, each term of this series is just a typical term of this function. So the integration here is what? Is just the integration of the terms in a series, Taylor series, term by term. When n equal to 1, we have this term. N equal to 2, we have this term. Understand? So when we talk about the integration of these special terms, actually we are integrating a analytical function. And in fact, this analytical function can be arbitrary. All of the analytical function can be expressed in this way. Okay, and it can be integrated in this way. So we integrate this function along a circle, and then we have the integration term by term. Okay, but for every term, the result is just equal 0. See here, z minus 0 power of 2, the result is 0. I'm talking about the calculation in the last line of this blackboard, in the lower part. Please concentrate. The integration of z minus z0 with power 2 equals 0. Z minus z0 with power 1 is 0. For the constant term, z minus z0 with n equals 0, just like this, the result is also 0. So each term after the integration becomes 0. So what it means? Means that the integration of this function along the circle is equal to 0. But this result is a very general result because this function is an arbitrary analytical function. Understand? So the power of this formula now is clear. Because we have this formula, we can prove that the integration of any arbitrary analytical function is equal to 0 along the, if you integrate it along the circle, any circle will be, the result will be equal to 0. Understand? So it is a very, very important result. Okay, I say that again, the final version. Integrate any arbitrary, analytical function, all of them, as long as it is arbitrary, it works. We integrate as long as it is analytical, it works. We integrate an analytical function along any circle, the result will equal 0. Understand? This is the important result we have.